Okay, seems like it's working. So I'm just going to send them the link now. So it seems like I just had to make another, try to make another live stream directly on the YouTube app. Okay, good. So let me send everybody the link. So it seems like I just had to make another, try to make another live stream directly on the YouTube app. Okay. Okay, excellent. So okay, so welcome to Math 54. Just check that that's working. Yeah. Okay. And let me start recording this. So okay, so let me just say a little bit about the mechanics of the course before I start getting into the material and what we're going to cover and why it's interesting. So so what are the main resources in the course? So there's a lecture, which is at this time on Zoom. And this will be recorded and posted on B courses. So you can either watch it during the lecture. The advantage of that is you get to ask questions. Otherwise, you can watch it on B courses. Then there's a discussion section with your GSIs on Monday, Wednesday, Friday. And this, I mean, this course goes at a very fast pace. So it really is, I think, necessary to go to the discussion section. So you'll do problems. I mean, you've been to discussion sections in other classes. Then there's going to be office hours. So my office hours are going to be Tuesday 1 to 2 p.m. and Friday 4 to 5 p.m. And then the GSI office hours are posted on B courses. And you can go to any GSI's office hours that you want. Okay. Then finally, there's, or not finally, there's Piazza, which is an online forum for asking mathematical questions. And, you know, feel free to ask other students. I mean, generally the response time for this is pretty good. It's under an hour. So either one of us or some other student or GSI will answer mathematical questions on this. Then there's B courses on which I will post lecture notes from every lecture, in addition to the recordings. There's grade scope, which we will use which we will use for all assignments, for homework, quizzes, and exams. I'll say more about those in a moment. And then, of course, there's a textbook, which is a combined, it's actually a sort of mashup of two textbooks. Lay for linear algebra, 5th edition, and Nagel, Saff, and Snyder, 9th edition. And most of the homework will be assigned from from these textbooks. So I'll talk more about what the deliverables are for the course on the next slide. Okay, a lot of people are saying they don't have Piazza yet. Don't worry, you'll get an email about that and how to set it up. And finally, there's a course web page, which is linked from my web page. So that's okay. So I guess I haven't introduced myself. My name is Nikhil Srivastav. And you can just call me Nikhil. And the course, the course webpage has all of the course policy, links to all the lectures. I'm sorry, links to all the readings. So in particular, it has a schedule of readings. And the course policy are all on the course webpage. So these are the different resources for the course. And what's the workload for the course? So I guess what do you have to do in the course? So there's daily homework. That are posted on the webpage. And these will be due the following Wednesday on Gradescope. And these, I mean, since the material is moving pretty fast, and as in most of math, you really learn by doing, the best time to do the homework really is on the day of the lecture. Then there's going to be a weekly take-home quiz. On grades that's going to be released on Gradescope on Wednesday, and it's going to be open for at least 24 hours. So it's not really a timed quiz. It's not going to be very long. It should take about half an hour to do it. And this, I mean, really, you should think of this as, so these are problems that are going to be maybe a little bit more involved than the homework. They're going to be closer to what the problems on the exams are going to be like. And you should really think of them as, challenge problems to make sure that you really understand the material. And these will be graded. These will be graded by the GSIs, and you'll get written feedback on them. So this is your main mechanism for getting feedback on your level of understanding in the course. The homework is only going to be graded for completeness. Whereas this weekly take-home quiz, we'll actually look at it carefully and give you back comments. Then there are going to be 2 midterm exams. The dates are posted on the course webpage. The dates are February the 5th, February the 18th, and April, I believe, the 6th. And these are also going to be take-home 36-hour exams. So there's not going to be time pressure. All this stuff is open book. There will be an honor code, which means you have to sign something. You have to do the work yourself, and only use the resources in the class. But everything will be open book. And then there'll be a final exam whose format is not yet totally determined. This might be part of it, might be timed. This is the only synchronous thing in the course, really. And well, okay, I mean, of course, you should attend the discussions and so on. Those are also synchronous, but this is the only test which is timed. And of course, we'll make accommodations for different time zones, so don't worry about that. So those are the deliverables. How much they're worth is roughly as follows. So the homework is worth 5%. The take-home quizzes are worth 15%. The midterms are worth 20% each, and the final is worth 40%. And there's a policy of dropping the bottom two homework and quizzes. And there's also a policy of replacing the lower midterm by the final, if it helps you. And there are more details regarding the course policy posted on the course webpage, and we'll talk more about them as the exams approach. But I don't want to spend too much time on the logistics. So basically, this is the workload for the class. Typically, people say they spend 5 to 10 hours a week on this class. There are quite a decent number of homework problems. So, okay, that's a rough sketch of the mechanics of the course. So let me now move on to the content of the course, which is a much more interesting part of the lecture. Okay, somebody raised, oh yeah, okay. Does anybody have any questions about this? So I don't want to answer very detailed logistical questions right now, but
yeah, I raised my hand. Can I ask?
Yeah.
Okay. So would you expect the final to take the whole 36 hours, or is it like a
no
2-3 hour kind of thing? Or
yeah. So the exams are going to be normal length exams. They're going to be like maybe 3-hour-long exams. They're going to be on the they're going to be harder than they used to be 3 years ago when we had timed closed book exams. They're going to be similar to what I did last year when we did it online in the same way. They're going to be open book exams that should take maybe 3 hours to do. They're not going to take 36 hours. Yeah. Any other?
ठीक है ना.
कार्पेट है क्या पूरे रूम में?
Okay. So let me now.
बाथरूम हाल कैसा है? साफ सुथरा है?
Sorry, I think somebody's needs to be on mute probably. So let me.
अब कम्बोर्ड कौन साफ करता है?
जरूरत नहीं है ना टॉयलेट बोला तो टॉयलेट बोल के ले
ले आई वो डाल रखी है.
How do you mute all?
रहने देते हैं फिर फ्लश कर देते हैं क्लीन हो जाता है.
अब बाथटब ये सब पोंछ के छोड़ती हो कैसे छोड़?
Vansika, you're unmuted.
So let's see. How do you?
धीरे-धीरे थोड़ा.
Okay, good. I think I see who's. Okay, good. Okay. So okay, so let's start talking about the course. Okay, so what is the course about? So the course is about linear algebra primarily. And there are many ways of defining what linear algebra is. But one reasonable definition is it's a branch of math which studies systems of linear equations. So study of linear equations. And certain types of functions which are linear transformation, which are called linear transformations. Between vector spaces. Okay, so we're going to start by talking about linear equations. That's what we're going to do in the first couple of weeks. That's the most concrete thing. And then later on, we're going to see that this is related to a very important class of transformations called linear transformations. And concretely, here's what will you learn in this course? So you can broadly break it up into 3 types of things. So the first thing you learn is you learn some very concrete algorithms for solving linear equations. So there are type of equations, and you just want to find the solution. So that's similar to things you've done in math before. And these algorithms will allow you to manipulate some related objects, namely vectors and matrices. Okay, so these are procedures for solving a certain kind of problem. But then the beautiful thing, which maybe is different from other math courses, is that these procedures will actually themselves, have lots of interesting properties that will generalize to a setting that's much, that's much more abstract and covers many more phenomena than just linear equations. So the second thing you learn is an abstract framework for reasoning about linear transformations. And really, the way you should think about this is it's like learning a new language. Unlike maybe what you did in calculus or other math courses, we will define a number of concepts totally essentially from scratch. And this will be this new language of linear algebra. And then finally, you learn about differential equations, which are obviously related to calculus, but we're going to view them through the new perspective of this language of linear algebra. And they're going to turn out to just be a special case of, an important example of linear transformations. And all these things are going to be kind of connected in, I think, quite surprising ways. So, for example, a lot of the abstract theorems that we're going to prove about linear transformations, we're going to prove them by looking at this very concrete algorithm for solving linear equations and studying its properties. And similarly, all the stuff about differential equations, we're then going to use these properties to reach some conclusions in differential equations. So that's a rough outline of what's going to happen in the course. Roughly, the first part is going to be up to midterm 1. The second part is going to be between midterm 1 and midterm 2, and the last part is going to be after midterm 2. So these are going to be roughly separated by midterm 1 and midterm 2. Although, yeah, okay. So before we do that, I mean, before you invest so much energy in doing this, we should, well, I should tell you, I should try to convince you that you should learn this. So why should you learn linear algebra? So there are a number of different kinds of answers you can give to this question. So the first answer is that it has just a shocking number of different applications in different areas. So, for example, in physics, you might be, you might be interested in understanding how waves propagate. So, how do waves propagate in water? What happens when you pluck a guitar string? You might be interested in how heat propagates, so the heat equation. You might be interested in quantum mechanics. So maybe you don't already know what that is, but one specific thing is maybe you learned in high school that if you have an atom, then its electrons live in certain, well, orbitals, right? So these are all really fundamental physical phenomena, and they're all ultimately explained in the language of linear algebra. Like when I was in high school, I remember learning organic chemistry and being like, what are all these weird shapes of orbitals? And I never really understood why they're like that until I studied linear algebra. So if you're a scientist, then this is sort of very fundamental. And then maybe you're not a natural scientist, maybe you're a computer scientist. Probably many people are computer scientists. And here, I mean, many of the most important modern algorithms are in some way based on linear algebra. For example, how does Google rank its search results? That's actually something we'll learn in chapter 5, roughly the high level idea. How does Netflix predict, or tell you which movies to watch? This also has its roots in some linear algebra concept. Okay, I mean, there's a huge list, right? There's like how does MP3 work? I don't know if people use MP3s anymore, but how does audio compression work? How does deep learning work? You may have heard about that. All of these things are really written in the language of linear algebra, and it's safe to say that there's no other branch of math. This is probably the most important branch of math for you to learn if you want to learn any of these things related to machine learning. And then there are applications in statistics and economics. For example, if you want to learn about how do you design randomized controlled trials, like experiments. For example, right now, there are all these experiments going on to determine efficacy of COVID vaccines. How do you actually design those experiments? So that's a statistics question. And that ultimately, the theory around that is written in the language of linear algebra. And then, okay, if you're a game theorist, you may be interested in equilibria in games. This is also ultimately written in the language of linear algebra. So this is very relevant no matter which of these paths you want to go down. But I mean, I don't know. For me personally, the reason that I love linear algebra. So by the way, my area of research is linear algebra. I mean, I really spend most of my time thinking about eigenvalues and eigenvectors that you learn about in chapter 5. And for me, the reason I find this so amazing is that it really, linear algebra articulates certain patterns that exist in so many branches of science and of math that I really think of this as exposing a hidden layer of reality that really unifies my understanding of how the universe works. So a picture that I often, show when I begin to teach this course is this. So where is that? Yeah, okay. So this is a picture from The Matrix, which I don't know if people still watch The Matrix. Has everybody seen The Matrix?
Yes.
Okay, so this course is about matrices, but The Matrix is also about how the world is not really what you think of it is, and the underlying mechanisms of the world are somehow different from what you can actually see. And linear algebra, I mean, the thing that really amazes me about it is that it's so pervasive that the patterns of linear algebra really are in some ways the deepest explanation that I have found for how the universe works. And so I think that's a good reason to study it. And then finally, another reason you may want to study it is it's just a very beautiful subject. And one way of maybe articulating what's so beautiful about it is this picture here. Okay, so this is like some kind of a fable where there are a bunch of people with a blindfold and they're all, touching an elephant, and each of them thinks it's a different thing because the different parts of the elephant are so different, and yet they're all actually really, they're all the same thing and they're all connected. And this is also how you will see the material in this course coming together, that we'll learn a bunch of different things, but it's all but they're all they're all in some sense different perspectives on the same underlying phenomena. And the level of interconnectedness in linear algebra is, I would say, it's deeper and it's sort of more stunning than maybe what you've seen in calculus or areas of math that you did before this. So I think it's a sort of a beautiful object to study. So that's why you would study it. And well, I don't know, any questions about that? Okay. And throughout the semester, I'm going to actually do a bunch of demos to show you some of these applications, so you can actually see you can see this instead of just believing me. Okay, so let's actually get started with the course in that case. So the first topic we're going to study is linear systems. So what's a linear system? So it's a bunch of linear equations. What's a linear equation? What's a linear equation? So a linear equation is an equation that can be written in the following form. So sorry, I think someone's mic is unmuted again. Yeah, okay. Well, okay, I think I'll just mute all. Yeah. Okay. So it's an equation that can be written in the following form: a1x1 plus a2x2 up to an xn equals b. And now what do all these different things mean? So where these AIs are numbers. Okay, so numbers means that they're either real or complex. And these x1 through xn, sorry, this should be n, are variables. So these are unknowns. And this is called a linear equation in n variables. So the important parameter associated with this is the number of variables, n. And a linear, okay, so what's an example? Maybe let's see some examples. So this is a linear equation. This is also a linear equation. It's not exactly in the form that's written above, but notice that the definition says can be written this way. And one property of equations, a basic property of equations, is that you can rearrange things across the equal sign. So indeed, this second equation can be written in the form listed in the definition. And what are some non-examples? Well, anything where you multiply variables is not a linear equation. Right? There's no way of rearranging this, so it's equal to some numbers times the variables added up equals some other number. Similarly, if you do things like take sine or exponential, there's no way of rearranging these to write them as a linear equation. So by the way, I'm noticing a lot of questions in the chat. If you have a question, feel free to just ask, like just unmute yourself and ask the question, because it's hard to look at the chat because there's a lot of other stuff happening in the chat. Yeah.
Wait, so R is real numbers, and then what's like the cent sign looking thing?
Okay, yes. So this is real numbers.
Yeah.
And C is complex numbers. Okay, so for the first half of the course, these will always be real. So if you're uncomfortable with complex, don't worry about it right now. We'll do a mini review of complex numbers later. Okay, so these are examples and non-examples of linear equations. And a linear system. Any other question, by the way?
Professor, for the second example, where is the fourth unknown? Is it like 1 or something?
No, there is no fourth unknown in the second example. So that's a good question. In the second example, I'm using the fact that this is equivalent to, if I just move the 9 to the other side, this is x1 minus 5x2 plus pi x3 equals minus 9, right?
Oh, yeah.
And that's now, because remember the definition says can be written as. Okay.
Okay, thank you.
Good question. Yeah. Okay. So one linear equation is not a very complicated thing. The more interesting thing is a bunch of them all together. So here's the second definition. So a linear system in n variables is a collection of linear equations. So it's a finite collection of linear equations. In those variables. So i.e. it's a bunch of equations of the form so I'm going to write it this way: a11 x1 plus a12 x2 plus dot 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 a1 n xn equals b1. So that's the first equation. But now I'm going to have a bunch of these, let's say m of them. So then the second equation, I'm going to write the coefficients as a21 x1 and then let's say I have m of these. Okay, so there are going to be m equations. Okay. And what we're interested in doing is, given a bunch of these equations, finding their solutions. So what's the solution? So so a tuple just means a bunch, a list of numbers S1 through Sn is a solution of a linear system if setting the variables to be equal to those values makes the equations true. And what we're going to be interested in this course, which is certainly a bit of a departure from high school mathematics, is given a linear system, we're not just going to want to find a solution. We're going to want to find all the solutions. Okay. And that's called the solution set. So the solution set of a linear system, okay, is the set of all solutions. So we want to find all settings of the variables that make all the equations true, not just one. So let's look at some examples. Okay, so the basic question we want to answer is, given a linear system, find its solution set. So any questions about this definition?
Can you like elaborate a little bit on the definition of like a tuple? Like I still don't think, like I get that like the linear system is like a bunch of linear equations, right? And then I don't get like where the tuple comes in from, or tuple, sorry, tuple.
So a tuple is just a list of numbers. So and again, it must be specified that they're real or complex.
Okay.
So you could be looking for real solutions, or you could be looking for complex solutions.
Okay.
So I mean, yeah, formally it's just a set of, lists of real numbers or complex numbers that must be specified in the problem, which make the equations true. So are you feeling that that's still too ambiguous?
No, I understand it
Okay.
now.
Mhm.
Thank you.
Yeah. And again, you have to specify whether you're doing real or complex. But let's look at some examples. So the first example is, let's look at this linear system, x1 plus 5x2 equals 6, and minus x2 equals 7. So in this case, the first thing you should ask when you see a linear system is, what's the number of equations, and what's the number of variables, and what's the number of equations. So number of variables is 2, number of equations is also 2. And okay, right now this is easy. We know how to solve this. The second equation is just telling us what x2 is. It's minus 7. And the first equation, we just substitute. We get x1 plus 5 times minus 7 equals 6. And then if you just plug this in, you get x1 equals 41, x2 equals minus 7. And these arrows are, implications, right? This is saying if these two equations are true, then the conclusion has to be true. Okay, and actually these are two-way implications, right? So so actually the solution set of these two equations consists of just one point, 41 comma minus 7. Okay. Let's look at another example. Let's look at these equations. x1 equals 6, x2 equals 4, x1 plus x2 equals 0. So that's a valid linear system. N equals 2, m equals 3. And I don't know, just looking at this, anybody have a sense of what the solution set is?
No.
No, yeah, there are no solutions. Why? Well, the first equation says x1 has to be 6. The second equation says x2 has to be 4. And 6 plus 4 is not equal to 0. So this has no solution. And so the solution set is the empty set. This is called the empty set. Okay, I noticed in the chat, people are confused about what m is. M is the number of equations.
So n is the number of variables and m is the number of equations, right?
Yeah, there are two parameters. N is the number of variables and m is the number of equations. And those are different. Those may be different. Okay. Okay. Any questions about these examples? Okay, let's look at a slide. Yep.
When we're working out the solutions, are the arrows necessary, or is that just like for explanations? Or
So right now I haven't developed a general methodology for finding solutions. We will do that in the next lecture. And in general, you want to use a systematic procedure. Right now, I'm just doing some ad hoc procedure, right? Substituting one equation in another. The arrows are necessary in order to say that the solution set is equal to this, because this arrow, by the way, means if and only if, right? It means the two statements are equivalent. And, you know, I mean, what this is saying is that the three linear systems that are written are actually equivalent. They have the same solution set. And I do need that equivalence to conclude that the solution set of the last system is equal to the solution set of the first one. So, I mean, for example, if I just put a one directional arrow, I could have done that and thrown away one of the equations, right? But that would not have preserved the solution set. So that's what the two directional arrows mean, that they're equivalent in both directions. Does that answer the question?
Yes, thank you.
Okay, so let's look at example 3 now. Let's look at this equation, x1 plus x2 plus 3x3 equals 2. So in this case, there are 3 variables and 1 equation. That's perfectly allowed. A linear equation itself is also a linear system. And well, how would you find the solution set of this?
Rearrange the variables.
Rearrange the variables, okay. But how? Okay, so what rearrangement would you do?
So x1 would be 2 minus x2 minus 3x3, and x2 would be negative 3x3 plus 2 minus x1, and then x3 would be 2 minus x1 minus x2 over 3.
Okay, so you're saying you can rearrange these equations in a bunch of different ways, right? You can get 3 different equations, but that doesn't actually write that doesn't give me a description of the solution set, right?
Would the solution set be?
Infinite.
You just wouldn't have any solution, right? It couldn't.
No, wouldn't it be infinity? Because there's like.
Yeah, it wouldn't be the empty set, but it wouldn't.
Yeah, it's infinite.
Okay, so you're already sort of getting at what I'm going to do next, but here's okay. How do you find a solution, right? So to find a solution, you can do the following. Just set x2 to be, or sorry, set x1 to be anything. So S1 is any real number. Then set x2 to be anything. But now you can't set x3 to be anything. But now you can set x3 to just be 2 minus x1 minus x2 divided by 3. Yeah. Right. And this, when you do this, you will always get a solution. And actually, all solutions have this property. So actually, the solution set, in this case, if you were to write it as a set, is a set of tuples that look like S1, S2, and then the third one is just 2 minus, sorry, this should be S's. So the reason I'm using a different variable is S is for some specific numbers, whereas X is for variables. So it's a set of all tuples that look like that, where S1 and S2 are any real numbers. Okay, so by the way, one thing that's needed in this course is set theoretic notation. So if you're not familiar with this, I'll post a handout on the website so you can refamiliarize yourself with this. This is the set of all tuples. And this symbol means such that, right? This colon. This is read as such that. This is all tuples of this form such that S1 and S2 are real. So in this case, the solution set is an infinite set, right? There are infinitely many points in there. So we saw 3 different scenarios. In the first case, the solution set had 1 solution. In the second case, it had no solution. And in the last case, it had infinitely many solutions. And so this is a general phenomenon, which I'm now going to articulate.
For a problem like this, would it be
Mhm.
possible to, instead of pinning down x1 and x2, pin down x2 and x3? Would that answer be okay?
Great question. That would be fine too. So you could also parameterize. So here's a remark. You could also parameterize it in terms of the second 2 variables. Parameterize just means describe in terms of some free. We'll say precisely what it means in terms of S2, S3, or S1, S3. You could do that. The point I want to make right now is just that the solution set is infinite. We'll talk more about how to describe it systematically later, but that's a great question. Another remark I might as well make before proceeding. The names of the variables don't matter. So I could write an equation in terms of x, y, z instead of x1, x2, x3, and that would still be a linear equation, right? At this point in math, I guess we're okay with that level of abstraction. And the second thing is you must specify whether you want solutions in R or in C. So this is part of the problem. You know, up till roughly half the course, we'll always be working in R. But you know, to fully specify a linear system, you do have to say, where are you looking for the solutions? Okay, sorry, I can see my handwriting is already getting bad because people are getting confused, so I'm going to start writing more clearly. But anyway, now these 3 examples exhibited 3 different kinds of behavior, and there's a general theorem saying that these are the only 3 things that can happen. So I'll now tell you what that is. So I'll call this the trichotomy theorem. And the theorem says that given any linear system, there are only 3 possibilities. So the solution set is one of the following. So the first possibility is that it's empty, no solutions. The second possibility is that, okay, or maybe I should write it like this. So it's either empty, or it has 1 element, exactly 1. Or it has infinitely many elements. Those are the only 3 options. So we will prove this in the next lecture or 2.
Go back to the remarks slide, like really quickly.
Yeah.
Okay, thank you very much.
So it must specify whether you want solutions in R or in C. Yeah.
Sorry,
Okay.
Could you read out what that first remark was underneath the one with the 1?
Oh, names of the variables don't matter. Names of vars don't matter.
Okay, thank you.
Okay, so this trichotomy theorem, we'll prove it later. Let's see why it's true in 2 dimensions, right? Okay, so in 2 dimensions, let's I'm going to explain it geometrically, and this is a running theme of the course, that a lot of the things we're going to do look algebraic, but there's a geometric picture behind them. So let's consider, I don't know, m equals n equals 2. Let's just prove a special case of the theorem. So there are 2 equations. I'm going to call them E1. So A11 x1 plus A12 x2 equals B1. And then the second equation I'm going to call E2 is A12 x1 plus A22 x2 equals B2. So there are 2 equations. And I'm going to make, to turn this into a geometric question, I'm going to make 2 observations, which you're probably familiar with. The first is that that the set of solutions of each equation, of just one of the equations, what does it look like geometrically? So let's plot an xy plane or an x1, x2 plane. First observation is that the solutions of each equation correspond to a line in the x1, x2 plane. So this is just y equals mx plus b or whatever you learned. And what this is saying is that, well, if I, sorry, this is theorem. THM is just theorem. Okay, that doesn't make it any clearer. Let's. So if I plot 2 lines, so the first equation is some line. Let's corresponding to E1. That's a set of x1 and x2 values that satisfy the equation. And then the second equation is some other line. And so the set of solutions of the system is the set of points that lie on both lines, right? Oh, sorry, this should be 821. Thank you. Yeah. And so the solution set of the system corresponds to the intersection of the 2 lines. So the solution set of the system in this case, in this picture, will just be this point. But now, we're going to appeal to a fact about, geometry in the plane. And we're going to see that there are only 3 possibilities for 2 lines. So the first possibility is that the lines are parallel. And in this case, there's no intersection, right? So there's no solution. The second possibility is that they intersect at a point. And in this case, there's one solution. And the third possibility, which, okay, I should have said parallel, but not equal. The third possibility is that they're the same line. And in this case, there are infinitely many intersection points, right? So in 2D, there's this geometric picture related to lines, at least in the case of 2 lines, explaining why this happens. And a nice, thought experiment that, something you can think about after the class. I would have thought about it now, but because of time, because of what happened in the beginning, I don't think I can. Why is this true for m equals, for 3 equations in 2 dimensions? So 3 lines. And the second question, which is maybe even more interesting to visualize, is why is this true in 3 dimensions?
Professor, could you go back to the graphs real quick?
So yeah, the intersection point is in red. Here it's this point. Here the whole thing is an intersection because it's the same line. Okay. Any question about this?
Professor, does this rule only fits in the conditions given by Euclidean geometry?
Yeah, this is all related to Euclidean geometry. So yeah, if you're familiar with other geometry, this is not true. So this is, it's a good question. This is really a phenomenon of Euclidean geometry, which if you don't know any other geometry, then don't worry about it. But yeah. Okay, so you can think about these offline. What I'm going to do, what I want to do now is to do one more thing that's going to be a theme throughout the course, which is I'm going to refine the basic question into two sub-questions. So remember, the basic question was given a linear system, find its solution set. But I can actually refine this into two sub-questions that are both have very sort of interesting meaning of their own. The two sub-questions are existence of solutions and uniqueness of solutions. Okay, this is going to be an organizing, these two concepts, it's very important to get them right, and they're going to be a recurring theme throughout the course. So what does existence mean? Existence is the question, is there a solution? So in particular, that means, is there at least one solution? So I'm going to maybe circle this. So existence just means, is the does the solution set have at least one element? Is it non-empty? And uniqueness is a complementary question, which is asking, is there at most one solution? So maybe to write it more symmetrically, I'll write this as, is there at least one solution? And is there at most one solution? So is there at most one solution is the question, is the solution set, does the solution set have at most one element? And you can ask these, often you don't, I mean, in applications, but also in the development of this course, answering just one of these questions is in itself interesting. Okay.
Yes, sir.
Yep.
Does existence has be true so that uniqueness be true?
No,
or they
no.
can be?
This is very important. That's a great question and very important. So let me now revisit our three concepts, our three cases in terms of our new criteria of existence and uniqueness. Okay. So in the empty case, is existence satisfied?
No.
No. Is uniqueness satisfied? Is there at most one solution?
No.
Yeah. There are 0 solutions, which is at most one. So uniqueness is actually satisfied in this case. So there's a linguistic sort of confusion about this, which is when something has exactly one solution, you say that it has a unique solution, right? But in English, that terminology, there are actually two things going on there. One is that it has a solution, which means it has at least one. And it has a unique solution, which means it has at most one, right? So this is a common point of confusion. In this class, uniqueness means at most one. 0 is okay. Okay, you don't have to have existence to have uniqueness. You don't have to have uniqueness to have existence. Okay, so in the second case, there's at least one solution, And there's at most one solution, right? In the third case, there's at least one solution, but is there at most one solution?
No.
No, because there are infinitely many solutions. So rather than get confused by, linguistic issues, I encourage you to think of existence and uniqueness as being at least one solution and at most one solution. Okay, so that's existence and uniqueness. So now we're going to try to tackle this basic question. Okay. So how would you do that? Like suppose I give you 10 equations, right? How would you find the solution set, or how would you answer these existence or uniqueness questions? Not clear, right? So need to find a systematic way. To answer the basic question. And that's what we're going to develop in the next lecture. I'm going to show you an algorithm that does this. And this algorithm it's a very important algorithm called row reduction. And by systematic, I mean no cleverness required. Okay, so if I don't feel like I understand anything until there are no tricks involved, right? I don't mean this as in a derogatory way. I don't like cleverness. I like to understand things so that they're, you don't need to do something ad hoc to make it work. Okay, that's what I mean by systematic. Okay, so let's develop this. So first we're going to develop a new notation. A more compact notation for linear systems. So I'll just show it to you by an example. So let's say I write down a linear system like this. So minus 3x2 plus 4x3 equals 9. x1 minus x3, 3 equals 6. And minus x1 minus x2 plus 10 x3 equals 16. That's a linear system with m equals n equals 3, right? So the first thing I'm going to do is I'm going to add 0 times the missing variables. I can do that, right? That doesn't, just to make it more uniform. And now I'm seeing that writing it this way is actually kind of redundant, right? Like in every sentence, I'm writing x1, x2, x3 equals, right? I'm wasting a lot of ink or, whatever this is, by writing these symbols again and again. And so what I'm going to do is I'm going to develop a new notation which contains all of the relevant information and is more compact. And this is called an augmented matrix. So on the left-hand side, you had a linear system. Okay. And I'm just going to write the coefficients, right? The variable names are going to be implicit. So I'm going to write 0, minus 3, 4, 1, 0, minus 1, minus 1, minus 1, 10, 9, 6, 16. And now what does this mean? Well, the rows correspond to equations. The columns, so this is an array. The columns correspond to variables, right? So the position tells me what variable it is. The first position is x1, the second one is x2, the third one is x3. And the last column has a special meaning. The last column is the right-hand side. Okay. Now I have not lost any information by doing this. I can go back and forth, right? If you give me an augmented matrix, I can write down a linear system. If you give me a linear system, I can write down an augmented matrix. It's just a more compact way of writing the same information. Okay, so now with this new notation, now what is my strategy going to be to solve the question of finding solutions to a system of linear equations? So strategy is going to be the following. Given an arbitrary linear system, I'm going to transform it. So I'm going to to a simpler system without changing the solution set. So this is a very good strategy in life, right? It's just saying, i.e., make the problem easier without changing the answer. Okay, so to do this, we need to know two things. We need to know what does transform mean and what does simple mean, right? What is a simple linear system? So to decide what simplicity is, let me just show you 3 examples. So example A is a linear system that looks like this. Sorry, X. Example B is where is this? Or actually, I'd like to have 3 equations. So let's do x1 plus x. Sorry, this is not x5. This is 5. Example B is just this. And then example C is this. Okay. So now let's take a poll. Which of these do you think is this? Which of these do you think is the second simplest? Actually, sorry, the poll says simplest. Which of these? Okay, we can all agree that this is the simplest, I think, right? The answer is just given to us. But between A and C, which one do you think is better?
For C, is the last equation supposed to say x5?
Oh, sorry, x3. Yeah, x3.
Can you give us the option to do the survey again? Because I thought
Okay, yeah. No, I changed the survey in the middle. I mean, let's do it again. Okay. Okay, let's do it again. What's the second simplest one? I'm just trying to get a gut reaction right now. We will define what simple means. Well, I guess in the next lecture, since this lecture is almost over. But okay, the overwhelming majority of you agreed that C is the second simplest one, right? So let's end polling here. Now, why is that? Well, you can see it if you draw it as an augmented matrix, right? So this one looks like. So I'm just going to not draw the zeros. And then there's some stuff here. This one, well, looks great, right? This just looks like this. And this one looks kind of maybe a little bit more. You know, Again, I'm not drawing the zeros. Okay. And probably many of you realize the reason this is simple is that the pattern of non-zero entries is very special in this case. It forms a triangle.
Identity matrix.
Yeah, and this is, of course, the simplest one. This is the identity matrix. But the punchline, which I will make precise in the next lecture, is simplicity lies in the pattern of non-zero entries. Of the augmented matrix. And what we will do in the next lecture is show how to start with, there's some nice set of simple linear systems. We'll show how to start with, an arbitrary one. And we'll show how to do some systematic steps to transform it into a simple one. And then the answer will be obvious. So anyway, that's the end of the lecture. I'm sorry for starting late. I will have this issue resolved by next time. And yeah, the first discussion section is tomorrow, as I will also announce now. The first discussion section is tomorrow, but see you on Thursday.
All right. Thank you. Have a nice day.
Thank you.
Thank you.
Bye. Thank you. Have a great day.
Thank you.
Thank you.
Thank you.
Professor,
If
could you
anybody
go
has
back
any
to the,
questions, you
Thank
can
you.
ask also.
Where's
You.
could you go back to the slide with the augmented matrix example, the
Yes.
first time you showed it?
So the augmented matrix example. You mean this?
Oh no, the first, yeah, that one.
Yeah.
Okay, thank you.
Excuse me.
Professor,
Mhm.
I think someone asked this in chat, but will the notes be posted somewhere?
The notes will all be posted on B courses.
Oh, okay, thank you so much.
Yep. Thank you.
Oh, Professor?
Yep.
Can you go to the last slide that you presented?
Yeah.
All right. Thank you.
The last thing I wrote is a cartoon of what the algorithm is going to look like.
Oh.
You're going to turn some arbitrary problem into a simple problem. And simple is somehow going to depend on the pattern of non-zero entries.
Professor?
Yep.
I have a question about the homework.
Yes.
So when we do the homework problems, are we just gonna like write it down on a piece of paper and then submit like a copy of our work, or
no, so you are not. So you're going to submit, you can write it on a piece of paper and submit it on Gradescope.
Okay.
So if you've not used Gradescope before, I've posted a link to instructions on how to use Gradescope on the course webpage. But now that you've brought it up, I'll send out an announcement also if you haven't done that.
Okay, sounds good. Thank you.
How long after each lecture do you expect to put up the recording on B courses?
I think within an hour, like Zoom just needs to like encode it or whatever, I think. So
cool, thank you.
It'll be like very soon.
So when do we are the homework assignments already up on Gradescope, or like are you gonna like send out like logistical?
Sorry, the homework assignments are up on the course website, as I mentioned in the first slide of the lecture. So the homework, the daily homework problems are posted on the course webpage.
For the problems that are posted on the homework, which textbook are we using first?
Oh, Lay. So I think it should. Oh, I see. It doesn't say that. Okay, you're using the linear algebra textbook Lay.
Okay.
Thank you for asking. Yeah, I'll say that.
Thank you.
Anything else?
Can we type up our homework, Professor?
Oh, if you want, sure, but you don't have to.
Okay.
But yeah, if you want, I'm sure nobody will mind.
Professor?
Yeah.
I was wondering why like the reasoning behind the definition of unique, especially in the case of no solutions.
Yeah, so the reason is that Well, it turns out really we want to decouple these two concepts. So it turns out that there are going to be very clear criteria for uniqueness, which are much clearer than if you ask the question of existence and uniqueness. So, I mean, I mean, okay. The high level answer is in math, we can define things any way we want. And the good definitions are the ones that lead to clear patterns. Okay. So that's why we define uniqueness this way in math, because you end up with much clearer theorems and understanding of what the mechanism is that causes uniqueness. Now you may be wondering why in English something is for something to be unique, it has to exist, right? Maybe that's what's bugging you.
Yeah.
Yeah, but I mean, I think maybe the answer is that the definition of uniqueness in math is done this way in order to basically just produce cleaner theorems, I would say. Like in the sense that we'll prove theorems like, if such and such happens, then uniqueness holds, right? That's a much cleaner theorem than saying if something happens, like uniqueness will be equivalent to a number of other properties, whereas existence and uniqueness together does not have such clean characterizations. So in some sense, we define uniqueness this way because it leads to more beautiful mathematics.
Okay.
I don't know if, I mean, is it a philosophical? So are you asking just sort of a sociological philosophical question, or are you asking a math question?
I think I'm asking more of the second.
Yeah, so I mean, okay. Maybe the point to clarify is I wouldn't say something has a unique solution if it has 0 solutions. Why? Because has implies existence.
Yeah.
Right? So does that help answer your question? So I'm never going to say something has a unique solution if it has no solutions.
Okay.
But I can say uniqueness is satisfied.
Okay. Yeah, I think that
does that answer the question?
Sense.
Yeah. Okay.
Yeah.
Yep. Any other?
Do you have any tips for like studying? But
do you have any tips for what?
like studying, doing well on your course, taking notes, doing homework, that kind of.
So you don't have to take notes because all the notes will be posted online. I do encourage you to ask questions, to go to office hours, and to talk to other students. So I guess I should make this clear in the next lecture. You're welcome to collaborate with other students on the homework, though not on the quizzes. And one of the best things you can do is explain something to somebody else. So I would say, yeah, keep up with the homework and at least skim the reading before the lecture. That's another thing.
Professor,
Yep.
I think someone asked this already, but which textbook are we using for this? Like for today's homework?
We're using Lay, the linear algebra textbook. So yeah, so there are 2 textbooks mentioned here. Yeah.
Thank you.
Yeah.
Okay, Professor?
Mm-hmm.
So today's lecture is going to be on your website.
B courses.
So they'll be emailed us, or I mean, an announcement.
It'll just be posted on the syllabus. So I'll send an announcement saying that it'll be on the syllabus.
Thank you.
Yep.
Hi, Professor.
Yep.
I had emailed you a while ago in regards to my enrollment in the class and access to B courses. And I was wondering if you received it.
Oh, so let's see, what's your name again?
Sharon.
Sharon, okay. Yeah, so I will add you just now. Sorry about that. Yeah.
Oh no, it's okay.
Yeah.
And sorry, there's another quick question. So am I like free to like choose any discussion for now that I would consistently go to?
So that you have to decide with the GSI, because I think if they're okay with it, it's okay. But we just want to make sure that some GSIs don't end up with too many students. So just ask the GSI.
Okay, I'll email them ahead of time then. Thank you.
Yeah.